Well, good morning. It's 8:08 on a Tuesday morning, the 3rd of July. I guess this is the 4th of July Eve, and maybe some people are taking it as a vacation day. I don't know, but I know I'm the only one in the room. Sort of waited around for someone to show up, and so far no one has, so that's why I'm a little late getting started. But this is supposed to be differential equations, Math 238. We're in Chapter 2, First Order Differential Equations, starting this morning on 2.6, Numerical Method, a numerical method. There are many of them. This will be probably the only one we'll do, but the others build on this type of approach. There's actually a couple of approaches, and this is just one of those approaches. But if you sort of understand this one, it's not too hard to adapt to the other approaches as well. There were a couple of announcements I was going to make to you. I think most of you are transient students. I know of at least one or two that may be Lawson students. I know one definitely is. But I doubt if this announcement would apply to her anyway. It's concerning the Lawson State Community College Math Club /team. Most people, by the time they're in math, differential equation Math 238, they're awfully close to graduating. I know that's the case for her, and probably for any of the other Lawson students who are here. So more than likely you're not going to be here in the fall to participate. But if you are, if by chance you are, the Math Club team is meeting this summer every Tuesday afternoon. That's this afternoon included, as far as I know, from 4:30 to 5:30 over on the Birmingham West Campus. That's in the Science Building. That's the C Hall, C100. That's the end of the C Hall. C Hall is a very short hall. It goes between the library building and the academic building. And this is and it's on the side of the quad toward the baseball field, okay? And the C100 is the room closest to the library end of the building. C100 is on the outside of the quad toward the baseball field. C101 is on the inside. So C100 every Tuesday afternoon, 4:30 to 5:30. And this other announcement is for any of you. And I don't know particularly, well, I have a good idea why. Our career services program is always trying to find positions for students. And so I imagine they're the ones who forwarded this to us. But it's a private company, and I sort of hate, commercializing a private company. That's their job to do that, not the state's job. But they sent it to us, so let me just tell you about it. The company is called STEM Jobs, and obviously STEM stands for Science, Technology, Engineering, and Math. And it's an announcement of releasing a new tool to connect classrooms to careers. The STEM Type Navigator allows students to match their interests to opportunities. It says after high school, but I believe they probably mean after post-secondary, because the next thing they say is that. This company seems to be based in Pittsburgh, in an effort to connect students with opportunities from post-secondary institutions, employers, and the military. STEM Jobs has launched the STEM Type Navigator. Ask students about skills they like to use now in order to connect them to careers that use those same skills, according to the ONET codes from the Department of Labor. And so they're trying to make the job market more available, accessible, and understandable to students, basically. So I'll let you read this. Anyone who's interested. Looks like a good package. I just don't know why we're promoting it. But anyway, I'm not. I'm just making the announcement. Okay, so far nobody here, so let's continue. Well, let me get one thing updated in the book. Today, this is now July, and this is the 3rd. Okay, make sure I got that before I left off the week completely. Okay, So let's start section 2.6. Since nobody's here, I can't see who has a book, so I'll probably do too much reading here. Differential equation can be a source of information. That's what it's there for. We started the chapter by observing we could garner qualitative information from first order differential equation before we even attempted to solve the equation. Then in the last 2, 3, 4, and 5, last 4 sections, we've examined first order differential equation analytically. That is, develop procedures for obtaining explicit or implicit solutions. Okay? But guess what? Most of the differential equations that you'll probably ever run into in the real world are going to be probably pretty hairy, maybe a little bit indistinct and undefined, maybe not all that well posed, and to solve those analytically exactly is probably going to be a pretty tough bill to fill. Okay? So this section is going to introduce you to solving these differential equations numerically. Okay? And we kind of did this back in section 2.1, I believe it was, using the tangent line. Okay? And we did this very type thing. In fact, I think I'll go to the graph type image here. If you had a differential equation, and quite often they look this way, y prime, which of course means dy dx, or dy dt, or whatever it happens to be, is a function of some combinations of x's and y's. Okay? Not strictly a combination of x's. It could be y's only. Then it would be what they call an autonomous differential equation. If it's x's only, it's definitely a separable. But with x's and y's, it could be just about anything. Okay? And we even have an initial condition. In fact, to solve numerically, you almost have to have some type of initial condition. Y at x0 is equal to y0. Okay? Very generic. Okay? Did someone come to the door? I don't think so. Thought I heard something outside, but it may have been maintenance workers or something. Okay. The first assumption is this does have a solution. There's no guarantee it does, okay? But we'll assume that it does. So, where would we begin? Well, find on your graph x0, wherever that happened to be. It could be a positive x or a negative x. Somewhere on the x-axis, x0. And then at that point, the y value is y0. And then you go up from that point or down from that point, whether y0 is positive or negative, and you have a starting point somewhere there. Okay? Let's just say it's right there. There is x0, and this is your y0. Okay? So that's your starting point. Now, what we have in our differential equation here is at the point x0, y0, the function, okay, the function must be evaluable, okay? In other words, you must be able to evaluate the function. Otherwise, what good is it? You can't, if this function can't even be evaluated, you're sunk, okay? But if it's a function, usually it tells you what to do with the x's and the y's, so do those. And so your y prime, I'm going to call it 0, is equal to whatever your f of x0, y0 is. You know where x0, y0 is right there, and then your y prime would give you the tangent line, the slope of the tangent line at that point. Okay? So the one in the book shows something going up maybe like that. That's what your y prime at that point, x0, y0 tells you. Okay? Now, since you're going in that direction, then estimate where you're going next. And when you get a place that you can evaluate again, then evaluate your f, your derivative, the slope of the derivative of the tangent line at that new point, x1, y1, say, okay? And you keep doing that, and after a while, and you do it for several points. In fact, probably from this point here, evaluate all of them around. Evaluate it here, and here, and here, and here. See which way it's heading, okay? It may be that then from there, it seems like it's going either here, or here, or here, or let's see. Yeah, so just draw several of these things in, okay, and see what the trend is, okay? And then you can sort of backtrack and forward track and figure out approximately what the path of that particle might be, okay? Now, let's actually put some numbers to it, and hopefully we'll be able to do a little bit better. Now, I didn't bring a calculator today. I guess I'll need to run down to my office and get one. But let me set up here first, okay? So I'm going to erase some of this. Your f of xy here is going to be this function. 0.1 times the square root of y plus 0.4x squared. Goodness gracious. The pen won't come back. There it comes. 0.1 square root of y plus 0.4x squared. Okay, there is your differential equation, okay? And your initial condition, or starting point, whatever you want to call that, is this. That y of 2 is equal to 4. Okay, so let's clear out this stuff over here. Okay. So y of 2, when x is 2, y is 4. There we are. There's your initial value. Okay? Now that's a nonlinear, obviously, differential equation because of that square root of y in there. First order, however, non-separable. Looks like sort of a bear to do anything with. Okay? It certainly doesn't look like it would be conducive for exact differential. Certainly not autonomous. Certainly not, as we already said, not linear. Very few things I can think of you can do with it. Okay? Trying to think if it might set up for a Bernoulli. I don't think so. Okay? But it could. But anyway, there it is. And they state here, cannot be solved directly by any of the methods considered in sections 2.2, 2.4, or 2.5. They skipped 2.3, but I'm pretty sure it can't be done there either. Okay? But we can still get approximate values. Okay? Now, and here's where I need the calculator. So I'm going to put it on pause. And the only calculator I do have one on the computer, but going back and forth from it would be a real pain in the neck. Let me see if my little cheapie will work. So hold on just a minute. I'll go get my calculator. All right, good. I'm back. Sorry, that took a little longer than I intended because I got stopped in the hallway as normal. But we're just, another instructor was coming in, and she doesn't have any classes today, but I only have physically seen 2 instructors this morning. I saw a room that had students in it, so I'm pretty sure there's another one there, and I saw an office door open, but I didn't see the instructor. And I've seen in that room that had students, I think I saw maybe 3 or 4. You know, I'm sure there were more. I didn't stick my head in. And in this room, none, of course. And nowhere else up and down the hall have I seen a student. Okay, so pretty sparse here today. So anyway, let's start with the 0.24 and plug in and see what our y prime was at that value. Okay, so I'll use the same setup that I was coming with here. We will do y prime at when x is equal to 2. I didn't need a calculator for this one, did I? I will in subsequent ones, but for the very first one I don't. 0.1 times the square root of y. Y is 4, so that's 2. That's 0.2 plus 0.4 times x squared. Well, x is 2, so 2 squared is 4. 0.4 times 4 is 1.6 plus 0.2. So, I could fill this in, sorry. So your y prime there at that point, okay, I just did it in my head, and that was 1.6 plus 0.2, 1.8. Okay, there's the y, the first derivative there. Okay, so that's slope of 1 would be that way, 2 would be a little steeper. So 1.8 would be something about like that. Okay, now let's get a couple points up there. Let's do these two, okay, and see where it's heading there. So y prime at, we'll do 2.5. This is where I will need the calculator, okay. Whoops, I just had it right and turned it over. Now I'm using my phone, and my phone doesn't keep a great charge, so we'll do it while we can. I didn't know to bring a charger today, so I don't have one. All right. It's 0.1 times the square root of 5. Okay, I'll have to turn it this way. So let's do, we know it's 1.6, the second term is, that hasn't changed any. So this will be square root of 5. Let me make sure this is doing it right. Yes. Times 0.1 plus 1.6. All right, 1.82. So that didn't change very much at all there, okay? Let's go next door to the 0.35. So what? Let me write this down. 1.82. Okay. Y prime of 3.5. That's going to be. I should have saved the other part. Let's start with the 5 square root times 0.1 plus, and this will be, with its being, the x being 3, be 9 times 0.4 is 3.6. That's going to be 3.82. So up here it gets significantly steeper, way steeper. Okay? That was 3.82. Seems a little suspicious there, but we'll go with it. Okay? So it looks like next we probably need to look at, I don't know, say this point, that point, and that point. But you get the idea. Every one, identify a new point and go. And then you can come from behind. and do this point and this point, okay? And depending on how things go, you plot your path on backwards, okay, and get a series of these values. And you see the one in the book, and where x is equal to 0, because it's 0.1 times the square root of y, those are not 0, but they're very gentle slope. Now, when y is 0 and x is 0, there you do have a horizontal slope. We can draw that one in, okay? And the rest of these are just slightly positive, getting a little more as you go, okay? So those are fairly doable, really easily. You can do the others down here, but I don't think it's ever going to go that way. So you can then trace your path. It looks like it's getting steeper and steeper here and leveling off somewhere down here. And if you had plotted enough points down this way, you see it goes that way. Using the one in the book, that's what you get. But you see, it's really tedious to do all these points, okay? Each one you have to calculate the slope, approximate it, and then backtrack from there or forward track, wherever, to see if you can get a decent estimation of the path. Okay? Very tedious. So, therefore, get a computer to do it for you. And that's exactly what they did in the text. They generated this with a generated this with a I'm sure some type of computer program, and they just used the coordinates points to calculate the slope at every one of those tick marks, and then estimate what the curve seems to look like there. And I'm sure they can have a package to do that for you as well. Okay. Now, that's doing it sort of qualitatively, sort of like we did before. By the way, I was going to say, they do mention here using 0.24, the slope of 1.8, which is what we got, we can then do point slope form of a line, and we can come up with an equation of the tangent line that is y is equal to L of x. Okay? Now let's go back and just with what we had there, just going to wipe these out because I don't have a lot of room to write, and I need all the room I've got. Okay? We're basically linearizing the function. So that would be at the point 24, we're going to estimate, okay, your slope is 1.8, and you know you're going to be in the 0.24. So let's give an estimate of the line right here, okay? Slope of 1.8, we know that. So we have y minus 4 is equal to 1.8, that's the slope, times x minus 2, right? Point slope formula, that'll be the equation of your tangent line right there. So it would be y minus 4 is equal to 1.8x minus 1, let's see, 3.6. Yeah, okay? And then we'll add 4 to both sides, and you'll come up with y is equal to 1.8x plus 0.4. And that's what they got in the book. That is your best guess. So have your computer draw that line through that point, okay? Slope of 1.8, its y-intercept, it had come far enough back here, would have been down here at 0.4, okay? Of course, we're not going that far back, okay? Now, depends on how close you want it to be. If you want to do a very detailed search on it, then say, well, what would happen if we use a point 2.1? Just a little bit beyond 2, where is that line going? And we're going to go along this line to 2.1, okay? So plug in 2.1 for x here and see what you get your new y to be. We'll call that y1. Okay, so we're going to say x1 is equal to 2.1, just a little bit beyond where this x was here. So the y1 is going to be 1.8 times 2.1 plus 0.4. And let's punch that in and see what we get. 1.8 times 2.1 plus 0.4. I wish y'all were here to do all this punching away. Okay, 4.18. Okay, and that's what they got too. So at 2.1, they're going to be at 4.18. And frankly, on this scale of graph, I'm going to erase some stuff here. Okay, hopefully that'll be enough. Okay. At 2.1, that's just barely over your 4.18, somewhere up there. Well, you're right along that tangent line, it looks like. So, yeah, and you can creep your way along that way. And here at this one, you can continue this kind of process. Well, that's going to lead to what we call Euler's method. Okay, now let's go back to the white sheet here. So to generalize that procedure just illustrated, we use the linearization of an unknown solution y of x at of the differential equation that we had at the very beginning, y prime is equal to some function of xy. So we have the linearization of x is equal to, now that's going to be your y value. Think of that as your y, okay? y1, say. And that's going to be y minus y1, so the y minus y0, so move the y0 over here, plus your f of x0, y0. Now why f? Because that's your first derivative. That's your slope at that point, okay? Times x minus x0, okay? So I said here this is a y1. For right now we're going to call that our y, okay? New y value, okay? Later we may go back and do some other things with it. This is the point slope formula. All we did was add the y0 back to the right, so you have a linearization in x. Okay? Now, and here's where we do it. Your y1 then would be your L of x1, which is equal to y0 plus f of x0, y0 times, now this is where it gets a little bizarre. What is your x1? You're going to go over a little bit. Last time they chose 0.1, okay? So in other words, you're going to have your x0 that you know already, plus some small amount h, last time it was 0.1, minus x0. Well, guess what? The x0's go out, and that's just this function times your increment h, okay? So, what is your y1 then? The y1 is your y0, whatever it was before, plus that increment h times f of a previous, the next point, x1, y1. Now, they changed from x0, y0 to f of x1, y1, okay? Because you're now moved up to the next point, okay? And our previous example, this would have been 2.1, 4.18. And then you're going to the next y value. And then you plug and chug that way, okay? Now, this is just an approximation. Curves don't follow straight lines for very long. In fact, they never follow them, but they are fairly close to them for a fairly short distance. So the big deal here is the accuracy of this approximation depends heavily on the size of the increment h. How big are you advancing that x each time? A big h, you're going to have a big error really soon. Small h's, you're still going to wind up with an error, but they'll be a lot small. So usually we choose the step size to be, catch this buzzword or weasel word, I'll call it, reasonably small. Okay? Come up with a new tangent line, x1, y1, at x1, y1, and you go on from there. Okay? It's not actually a tangent line, but you do the same procedure with it. Okay? So, this leads to a recursive relationship, and here's what it is. Y of, they call it n minus 1, n plus 1. I want to make sure I use the same index that they did in the book, is equal y sub n plus h times f of x sub n, y sub n. Okay? Now, what is your x sub n? It's whatever your x sub 0 was plus n times h. Okay? You're incrementing along. Last time they were doing 0.1 steps at a time. Okay? You could have chosen 0.05. You could have chosen 0.5. You could have chosen any size step. Smaller the step, the closer your approximation is going to be. The larger the step, the more rapidly it deviates from reality. Okay? This is basically Euler's method. Okay? So, without the graph, let's use Euler's method to do example 1, which is the same one we had before. So we'll erase all this and we'll go back to our y prime is equal to 0.1 square root of y plus 0.4 x squared. Okay? At the point, and initial point, y of 2, goodness gracious, I can't write. Y of 2 is equal to 4. Okay. All right. Trying to kind of keep up with time here too, because without students to bounce off of, I completely get lost in time. Okay. So what we're trying to do is obtain an approximation of y at 2.5. So our goal is to determine y at 2.5. That's what we're interested in. We're going to start with h equals 0.1, just like we started before. Then we'll come back and do h equals 0.05 to see how much that improves things, if it does. Okay. So our formula, Euler's formula that we just had. But by the way, Euler was, you might wonder who in the world this Euler was. I can't remember if we've run into him before. One of the most prolific mathematicians of all time. I always put him and Gauss in about the same boat. My goodness, the two of them could just churn out papers and concepts and things like this. It's pretty incredible. Gauss was also a physicist type. Euler was a little bit more pure mathematician. And so some of the things he came up with were incredible. E, the base of the natural number system, that function that is everybody's favorite to differentiate and integrate, because e to the x, derivative of that is e to the x, the integral of that is e to the x. It's just a fun function, but it's the core function in our natural number system. So it's the base for your LN system, that number e. He discovered it pretty much. He identified it defined it, did all these kinds of things with it. And I don't know if he was conceited enough to do it or someone else came later and did it. They named the number, he calls it irrational number, similar to pi. Pi is 3.14159, blah, 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 and it just goes on forever without repeating a pattern. Well, the number E is 2.71, blah, 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 blah. It just keeps on going. An irrational number, so there's nothing you can really write down to represent that number except give it a symbol. Like they gave the symbol pi to pi, they gave the symbol E. Why the symbol E? Named after Euler. Okay? There's several Euler formulas, Euler equations, Euler everything out there. It's just really prolific writer. Now, I'm hoping I'm saying this right because I do get some of these guys confused. Seems like I remember a story about him that when he was like 4 or 6 years old, his father was an accountant, of course, good in mathematics and stuff, and he was doing his work at his desk, and Euler, very, very young kid, 4 to 6 years old, something like that, said, "Dad, you made a mistake there." And sure enough, when he went back and checked, he had. He was a child prodigy. Numbers just made perfect sense to him, and he did it from day one. I'm thinking he's the one that, and probably very early in his schooling, may have been the first year he ever attended school. I think his dad taught him mostly at home for a long time. When he finally did go to a public school, and I hope I've got this story right, the teacher that day was having kind of a bad day, not really enjoying teaching and not enjoying the kids making all the noise and stuff the kids make. So he thought, I'm going to get them quiet and have a little quiet time for myself. He said, write down on a piece of paper all the numbers from the whole numbers, counting numbers, from 1 to 100. Add them up, thinking that's going to keep them busy for a nice chunk of time. Well, Euler came up with the answer, the very much correct answer, in just a couple of minutes. And he thought, how in the world, did he know this, And but Euler, of course, very young age, has seen that 1 plus 100 is 101, 2 plus 99 is 101, 3 plus 98 is 101, and just kept pairing them off that way, counted the number of 101s he had there, and the last one would have been 50 plus 51 was 101, and multiplied those, because he already knew how to multiplied 101 by that number of pairs, which I think was either 49, 50, let's see, would have been 50 pairs, multiply 101 by 50, and there's your answer. Incredible mind for such a very, very young kid. And through his whole life, he was just amazing people with what he could rationalize, deduce, and if my memory's right, and again, I may be getting some of these guys confused, I think there was either some sort of accident or disease or something that he basically lost the sight in one eye, okay? But he kept on producing, prolific production, even after he was blind in one eye. The other eye, that's why I think it might be a disease, it started going bad on him. He continued to produce. He just had someone else do the writing for him, but he did all the work in his head. He had an incredible memory. He really didn't need to write down equations. He saw the equations, in his mind. And so even after he couldn't see, he was still almost as prolific a writer, with someone else actually putting pen to paper, but him telling him what to write, as he had been when he was fully visioned. Incredible guy. But anyway, he came up with this method way back, early in the development, say, of calculus. Okay? Sorry, that took way too long. So let's do a few of those. Okay? We know our starting point is 2, 4. We know that's going to be the case. And with an h of 1, we're going to calculate, using Euler's method, and I erased really more than I meant to, your y of n plus 1 is going to be y of n sub n plus 0. Well, I'll just leave the h there for now. Okay, I'm starting to plug in, but I haven't yet. Just set it up for you. H times your slope, which is going to be this value here, 0.1 times the square root of y sub n plus 0.4 x sub n squared. Okay? That's what we're going to use. We know our initial point, so we're going to plug that in. We've already done this one. Y sub n plus 1 is equal to 4 plus 0.1 times 0.1 times the square root of 4 plus 0.4 times 2 squared. Okay? We've already done that. That was 4.18. I think it came out pretty close to exact. Okay? Now, that becomes the y1. Okay? Because this was our y0, that's our y0, there's our x0. Okay? So to get y2, we have 4.18, that's your y1, plus 0.1, that's your step, times, in this part of the problem, 0.1 times the square root of your old y, your last y, which is 4.18, plus 0.4 times, you stepped up 1, so now it's 2.1. Okay. Now, I can't remember if we did that. Just to save my having to sit here and punch buttons, which would be extraordinarily entertaining for you at home, don't use the one they have in the book. Okay? So this will be our y2 based on that y1. Okay? Oops, I forgot to put my square up here. Okay. That y2 came out being 4.3768. Okay? So there's your new y2. Your y3 is going to be the y2, 4.3768, plus your 0.1 times 0.1 times the square root of 4.3768 plus 0.4 times 2.2, because you stepped up another tenth squared. Okay? All right. Pull out your calculators, do the math on that one, and they claim that you get 4.5914. Okay. So your y4, okay, now remember we're going to 2.5, that's where we're heading toward, and so far here the x is 2.2, this time it's going to be 2.3, we're going to do it a couple more steps, and we plug that in just like we did before, and the y4 comes out 4.8244. 4.8244. Okay? Then you do the same thing with that we were doing before, and your y5 is going to come out. And this is one you stop, 5.0768. Okay. Now, again, we don't know how close or far we are from what the answer is. Okay? That's just our best guess. Okay? Now, What if we're doing the same thing with h equal 0.05? We start the same way, okay? Your y1 is going to be your y0, which is 4, plus, but this time it's 0.05, not 0.1, times 0.1 times the square root of 1, square root of 4, plus 0.4 times 2 squared. Okay? And you can do that one almost in your head. Maybe not quite, but pretty close. And come out with a y1 of something considerably less than 4.18. This time it came out 4.09. Okay? Then the y2, we'll plug that value in there. The 0.05 there. This value we'll plug in there. And now we'll do 2.05. So I'll write that down maybe for this time. 4.09, okay, plus 0.05 times 0.1 times the square root of 4.09. Our writing is pretty lousy. Plus 0.4 times 2.05. squared. Okay. Punch those numbers in, and they gave you y2 to be 4.1824. Or is it 42? 42. Now, pause just a moment here and think. This is at value. Our y2 here was equivalent to our y1 over here. So you see they're fairly close. A little bit larger on the smaller cap size, which probably means, and I think if you remember how the graph looked, your initial slope line was undershooting what looked like the actual curve. So sure enough, the smaller increment, the closer you'll get to that curve line, okay? So you take this value, plug it back in there, move your next step up in the x, and you get y3, y sub 3. I'm just going to write these down. And in fact, I really want to pair it up with the x values at the time, but if I put those in, you'll think that's an exact value, so I probably don't need to. But this corresponds to 2.1. Okay? Well, actually, that one corresponded to 2.1 after you did the calculation. So this would be 2.15. Is 4.2826. Okay, y sub 4, which corresponds to your y sub 2 before. This comes up I'm having a hard time following in the book. 4.3854. Okay, now that corresponds to y2 before, and again, you see that you're leading it a little bit. You're with the smaller increment, you've got a little bit larger number, and that's because your initial slope, you might say, underestimated. The curve was going up faster than your tangent line was, by just a little bit. And therefore, this is. So your y sub 5, which would correspond to 2.15, no, 2.25, is 4.4927. 4.4927. And your y sub 6, when you plug that into the formula up above, sorry, 4.6045. Okay, now that pretty much corresponds to the y sub 3 before. And again, you're leading it slightly. Okay, that is a 4.5, not a 0.5. Writing sort of stinks. Y sub 7, which I think is then corresponding to 2.35. That would be 4.7218. Okay, and 4.8. Y sub 8. I don't know where that came from. Duh. Y sub 8. Okay. And I let my pen touch the page too soon, and I had something that looked like a minus sign there. It wasn't. Okay. Y sub 8, which is 2.4, is 4.8423. Okay, how does that compare here? Again, increasing a little bit faster, and again, because the tangent line is below the curve. Okay? Y sub 9, which is 4.5, corresponds to that, is 4.9686. And then I have to move over a little bit because it won't let me write in the very bottom of the screen here. So Y sub 10 is equal to 5.0997. Now, that corresponds to your Y sub 5 before. And you see we're still leading ever so slightly. Now, there's a part of me that looks at that and say, oh, I bet you it's going to be 5.1. Okay? I bet you that's what it really is leading to. We have no way to really tell that unless you have a computer actually do this for you, and I don't think that we have such a thing to measure against. So even though that looks suspiciously like it's converging on 5.1, I wouldn't bank too much on that. It could be. Sorry, I'm getting sort of congested here. Let's go for a little bit longer before, let's see. I don't know, this may not be a bad place to take a quick break, just so I can go clear my throat. So let's do that. We'll pick up with example 2. All right, sorry, I'm back. I don't know where the congestion's coming from, except with all the rain we've been having, I imagine there's probably quite a few molds and mildews in the air. And though I've never had many allergies before, treatment I'm getting sort of knocks my immune system kind of wacko, so it could be that this is coming from there. I don't know. So let's move on. Example 2. In example 2, we apply Euler's method to a differential equation for which we already have found the solution. So we do this to compare the values of approximating y sub n at each step with the true or actual values of y of x sub n of the initial value problem. So that will be our approach here. Let's clear the screen here and come up with the new. Consider the initial value problem, y prime, of course the dy dx, is equal to 0.2 xy. It seems like this may have been one of the first differential equations we did anything with. I don't remember what our initial condition was. I wouldn't be surprised if it wasn't this. Y of 1 is equal to 1. Okay? So it says use Euler's method to obtain an approximation to y of 1.5. So just, again, stepping up half a unit from here. And we'll first use steps of 0.1 and then 0.05, just like before. All right? Now, sorry, I can't talk. Again, Euler's method said y n plus 1 is equal to y sub n plus h times f. The h is your increment, and then your slope is going to be your f, which I think I'll, rather than wasting time writing it as f, I'm going to write it as 0.2 x sub n y sub n. Okay? Okay. Okay. So that will be our incremental step, how much it changes. Okay? Now, x sub 0 is 1, x sub 1 is 1. So your y sub 1 using 0.5, so here the h is, 0.1, okay? H is 0.1, and later we'll do h of 0.05. Okay, so y1 is going to be y0, which is 1, plus your h, which is 0.1, okay, times 0.2, that's from your problem, times 1 times 1, okay, because x and y is 1 for that first step. So your y1 becomes, this should be doable in your head, 1 times 1 is 1, so that's 0.2 times 0.1 is 0.02, and 1 plus that is 1.02. That's an exact answer, okay? And that would be your estimate for 1.1, okay? Now, your actual value, if you go back and do the math, okay, remember your actual value, I think I'll write it up here. When we did this before, y is equal to e to the 0.1 times x squared minus 1. Okay? Now, they say verify that. Okay. Let's do that. We probably need to, just for as a review type thing. Go back and rewrite this equation as dy dx is equal to 0.2 xy. Okay? Certainly separable. That becomes dy over y, if you divide both sides of that, is equal to 0.2 x dx. Right? Okay, this is log y. Okay, I'll put absolute values on it now because you really should do that every time you do a log. We're only going to deal with positive y's for a while now anyway. In fact, you can't tell looking at it. Well, we'll just leave it like that. Okay, is equal to, and this will be 0.1. I'll just do it the full way. 0.2 x squared over 2 plus c. Okay? We'll deal with the plus c in a minute. This is log y is equal to, this will be 0.1, 0.1 x squared plus c. Okay? Now, we have initial value, 1 and 1, so let's put those in. Log of 1, we don't need absolute values for that, that's obviously positive, is equal to 0.1 times 1 plus c. Well, log of 1 is 0, okay? So this is equal to 0.1 plus c, so c is equal to negative 0.1, Okay, go back and plug that in, and we have log y, I'll go on and put that back in, is equal to 0.1 times x squared minus 1, right? Because the c was negative 0.1, so that would have been negative 0.1 x squared plus 0 minus 0.1. Factor out the 0.1, and there you have that. Now take the e of both sides, and now you don't need absolute value anymore because e is always positive. Okay, and that'd be e to the 0.1 times x squared minus 1, and that is sure enough what they got up there. Okay, so we verified that. Okay, now I'll erase all that because I don't have room on the slide to keep it, but you see that's how we got that. All right, now separation of variables, usually the easiest, best way to go if you can do it. Okay, try it first. Okay, don't do anything illegal. You got to be able to justify all the steps, but if you can and they work, usually the easy way to go. Okay. Okay. Now, if you plug in x equal 2.1 here, then your y of 2.1, and I'll do it once on my calculator just to walk you through it, though you can't see it. Okay. All right. On my calculator, it's probably going to be easiest to do 2.1 squared, okay, minus 1. I'm going to do an equal, okay. Multiply that, and the only reason I do that is I don't trust my telephone to do it right, times 0.1, okay, I'll do an equal there too, okay, and then do the e of that number, okay, and then, yeah, I can't trust my calculator because it's not doing something right. Go back and try that one more time. It's 1.1. Go back and try again. Okay. Okay. 1.1 squared. I know what that is, so why am I even doing this? It's 1.21. Subtract 1 from it, and you get 0.21. Multiply that. Yeah, I did something wrong, I'm pretty sure, about 0.1. Okay, that gives 0.021. Yeah, this looks better. Take the e of that number. Yeah, and that's where we get the actual value here then is 1.022, no, can't write. I'm just going to do the first 4 digits like they do, 5 digits actually, 4 decimal places, 02122. Oh, I did too many. 212. Okay, they didn't do that last digit. 4 decimal places, 5 significant digits. Not that you really have that many. Okay, so you see we're pretty close, but not necessarily, not there yet. Okay, so we'll do a y2, okay, and that would be everywhere you see a 1 up here, you plug that in there and plug it in there for your y. I'll go on and do this one. Y sub 1 was 1.02. We can't go back and use that one because you're not supposed to be able to know that, okay? Plus 0.1, that's your increment, times 0.2, that was part of the problem. Now your x is 1.1, okay? That was the previous x, okay? And your previous y was 1.02. That's what we're using there. That's why I say we need to actually do this one, because so you'll get to see, because the x's and y's are awfully close to each other. Okay, without taking the time on the calculator, that comes out being 1.0424. 1.0424. Okay. Now, plugging that into our e function, we see that is now 1.0450. Okay, so as before it was a little bit greater, it's still a little bit greater and growing a little bit on you. Okay, y sub 3. Now again, you do all the same things. You plug this in there, you plug this in there, and you plug 1.2 in here. Okay, because that's your x value. Okay, now you get your y sub 3 to be, got to find it, there it is, 1.0675. And when you plug it into your actual value, you get 1.0714. Now, as we saw before, it's growing faster, but the rate at which it's growing is faster. In other words, it's getting a little bit further away each time because you're getting further from your original base. So your y sub 4, when you do that same thing, again, put it in the places it needs to be, you get 1.0952, but your actual value is 1.1008. Okay, so again, slightly increasing, and your y sub 5, which is your target value now, 1.1259 is your Euler method 1, and 1.1331 is the actual value. Okay, now let's go over to the other side and do your 0.05. This is the h is equal to 0.05. Okay, when you do that, your y sub 1 is going to be 1, just like before, plus 0.05 times 0.2 times 1 times 1. Okay? Okay, written that way, I don't need that last parentheses. Okay. All right, now this is something you can almost do on in your head. That's 0.2 times 0.05 will be 0.01, 1.01. That is your first estimate, and that's exactly what they got here. Okay, now we didn't do the e to the 0.05, we just did it with a step of 1. So to get something that corresponds to that, I think I'll just use it from the book so I don't have to do it. 1.0103. Okay, that would correspond to that. So again, not far off, you know, pretty good. And your next step here, y sub 2, plugging this value in all those. So let's do just one prototype, 1.01, that's for the y sub n, plus 0.05, that's our step size, 0.2, that was in the problem, we aren't changing that. Our new x value is 1.05, and the new y value is the one we just calculated, 1.01. Not from there, but from here. Okay, and you crank away at the numbers there. Pretty easy calculations, just doing it. And you get 1.0206. And this corresponds to that one, which corresponds to, yeah, to this one. Okay? And you see, with the larger step size, 0.1, you're further off from what your actual value is. This one gets you closer to the actual value, but still not there, okay? And the reason not there is your function is actually curving up faster than your derivative is, okay, which is a linear approximation. So you're going to undershoot it every time, and the amount of undershot is going to be more every time. So your y sub 3 is going to be the 1.5, okay, and that's going to be 1.15, sorry, 1.0318, I'm not going to write it down this time, 1.0318, and this will be the intermediate one of 1.0328. Okay, so you see again, you don't have anything to compare it to on the first because you didn't do 1.15, but this is, again, pretty close, but not bad. Your y4, plugging that in, you get 1.0437, okay, which corresponds to the 1.0424 before, but the 1.450 there, okay? So again, you're closer than you were with the bigger step size. With smaller step size gets you closer to reality, but you're still missing it. Okay, y sub 5 is 0.25, I believe it is 1.25. That's 1.0562. And when you plug that into your e function, the actual value, that was 1.0579. 1.0579. So again, see, you're fairly close, but the actual value is leading you, as always. Y sub 6, 1.0694. Okay. That corresponds to these here. So you see your, I can't read my writing there, if that's a 7.5, which I think it is, y3, yeah, 7.5. Not far off, but closer to the reality, but still below it. Y sub 7. 1.0833, and when you plug in 1.35 to your actual value, you get 1.0857. So you're staying pretty close to the actual, but you're constantly below it. Okay, y sub 8 with the 0.05, that is 1.0980, which corresponds to 1.10 here and 1.09 there. So again, you're closer than the previous, but you're still missing the mark. Y sub 9, getting real close to the end here, 1.1133. Okay? And when you evaluate that, 1.1166. So again, you're not far off. Not bad at all. Two significant digits for sure. One decimal place precision. Close to the second one, not quite. The 6 would have rounded that up to a 2. 3 wouldn't have. And you don't have anything to compare on the other one because you didn't do that. And then y sub 10, the last one, 1.1295, which is less than this, but better than that. Okay? So, my gut feeling on it is the smaller increment size, of course, is getting you closer to the other, but at this point, they're both drifting away from the other faster than they're drifting away from each other, it seems like. So they're kind of hanging tight because they're both linear approximations. The curve is moving on away. Now, they talk some about absolute error, and that is all really good stuff. The absolute value error is just the absolute value of your actual value minus the approximation. Since you're doing an absolute value on it, it doesn't matter which order you do. That's why they call it absolute error. If you did just error, it would be approximation. Let's see if that's right. Yeah, approximation minus actual. Okay, because if you're too high, that would be a positive error. If you're too low, that would be a negative error. Okay, and that would make sense. Now, but absolute error is absolute value, so it doesn't matter which order you do the subtraction. Okay, relative error is absolute error over the actual value. But again, do the absolute value of the absolute value, actual value, because you want your relative error to be positive. Okay? Now, the relative error is usually expressed as a decimal number, or you can multiply it by 100 and express it as a % relative error. You'll see it both ways in the literature, more than likely. Okay? They did that in their tables. I didn't carry it through here. But you see the having the step size almost uniformly, not uniformly, but pretty closely to, well, take that back too. By the end, you're half the relative error you had before. Early on, you were a quarter of the relative error you were before. So you see, that's what I was saying before, that the further you are from that initial point, the curve is curving up more than you're still using straight line approximations, so you drift further and further away. So your relative error gets a little bit worse as you go. Okay, now, of course that makes sense. Now they give here a caveat. Euler's method is just one of many different ways in which a solution of a differential equation can be approximated. Although attractive for its simplicity, it's seldom used in serious calculations, so why do we spend this much time doing it? Just to get you an idea of how it works. It was introduced here simply to give you a very first taste of numerical methods. We'll grow into greater detail in discussing numerical methods that give significantly greater accuracy, and notably the fourth order Runge-Kutta method, also called the RK4 method, fourth order. Okay, that's in chapter 9. Guess what, team? We're not going to get there. So if you want to do a more precise method, run over to chapter 9 and see that. There are other things they call numerical solvers, and these, if I'm not mistaken, go by two different names, and let's see if I can remember the names. One is the finite difference form, and the 1 is the finite I'm going blank on it. 1 is finite difference and 1 something else. It sounds almost the same. They take slightly different approach. And these are basically what they call numerical solvers. You just take your situation and model it, that differential equation, as, actually I'll write it in just like we did to solve it, and I've already erased that now. dy is equal to 0.2xy dx, okay? And what basically you do is choose your delta x, calculate it, see how your delta y is. If it's close enough, you're happy with it, go on. If it's not close enough, then take half your dx and go again. And really, what is close enough? Compare it to the last y you did. If your difference in the two y's you came up with is less than what you are going to be used as accepted level, 0.01, 0.001, whatever it's going to be, or percentage error, whatever you choose it. Whatever your marker is that you're going to let do, you go. If it's not close enough, you decrease your delta x again. That's sort of like a numerical solver. You just keep improving your delta x until you get a delta y that you feel like is close enough. Okay? The graph that's on page 80, and if you don't have a book, I'm sorry, I can't really do too much for you on that. It just gives you a little bit of a hint. And I think this is the same function we just did. I'm not absolutely certain, but it looks a lot like it. And I'll try to duplicate this curve. Clear all this off the screen. Okay. And here's your curve. At 0, 1, and they don't give us any other points. So I'm going to say 4, 5 is approximately on it. 1, 2, 3, 4. 1, 2, 3, 4, 5. Okay. And it seems like to me this is awfully close to an exponential. Okay, going like that. Euler's method creeps away from it slowly. Tries to stay close, but doesn't do that. I probably should have done that in a different color. This is Euler's method. Okay? The Runge-Kutta-Foer method basically makes it fit at the tick marks. Okay? At the... So it's far more accurate, but it's not precisely accurate. It's precisely accurate at those nodes where it makes it be true, but it does what appears to be a linear approximation from there. And it's not bad. Not bad at all. Much closer. And this book loves to point out weird things. A numerical solver of a function, and I think this is a maybe a discontinuous function. It can sometimes just drive you nuts, and that's what figure 2.6.4 is. Okay? Now, I'm not going to go into all that. That can eat up an awful lot of time. So there we finished 2.6. Homework exercises would be number 1. And by the way, these odd number problems, most of the answers are in the back of the book. So try number 1, try number 3, try do any of the odds 5 through 9, and try number 11. After that, the discussion problems you can try to think through. I don't think their answers are in the back. And computer lab assignment, I'm pretty sure that, well, it's not, it's an even number. Now, if you haven't had enough homework exercises to do in the exercise at the end of each section, there are some more. And again, the odd number problems have answers in the back. So you could do any of the odds 1 through 11. You could do you could do number 13. 15 or 17, any of the odds 19 to 25, either 27 or 29, or both, 31, 33, 35, 37, and 39. Okay? Again, you don't have to do those. If you just wanted a few more practice type problems to do, go for it. Okay, sorry. I got to stretch. That's one problem with your not being here, is I'm sitting at the table the whole time, and usually when you're here, I'm standing up sometime pointing out things on the screen. You're not here, so I'm not standing up enough, so I'm getting really, really stiff. Okay? All right, we only have a few minutes to go. Let's introduce you to chapter, wait, we're not doing chapter 3. Chapter 3 is modeling, and I don't think modeling was in our course description, okay? But I don't have that written down here. But I'm pretty sure we move on to chapter 4, okay? Now, chapter 3, that picture on the first page is pretty incredible. I'm guessing that may have been Mount St. Helens when she blew, but I don't know that for sure. They don't mention that here. So let's move on to chapter 4, and that is on page 118. What we're talking about here is higher order differential equations. Chapter 2 was first order differential equations, so here we're going to do higher order. Okay. Now, if you look at this, there are 10 sections in chapter 4. Now, we're not going to do them all for certain. Okay. We'll start with 4.1, preliminary theory, linear equations, okay? And then we'll look at 4.2, reduction of order, get it back down to first order that we can already know how to do. 4.3 is homogeneous linear equations with constant coefficients. And there is going to be the other. Remember back in chapter 2, I can't remember the section, 2.3 maybe? 2.4, I'm thinking. Nope, 2.5. I remember now, 2.5. Yeah. When we talked about homogeneous equations having the same degree of the polynomial type form. Okay? Now, in 4.5, that's 4.3, when we talk about homogeneous equations, we're talking about all of them equal to 0. So, again, same word, different meanings. Now, 4.4 and 4.5, they have two different approaches to the problem. And I've done both of them, and it seems like students respond better to 4.4. So that means we'll probably only do 4.4. If we have time, we'll move on to 4.6 then, skip 4.5. You can catch up that on your own. And I wish we had time for 4.7. I don't know if we will or not. But guess whose name shows up again? Euler. It's Cauchy-Euler equations. But again, I'm guessing we're not quite going to get there. All right. So that's blah, blah, blah about what we are or are not going to do. I ran out of time before we got to start 4.1. So we'll start 4.1 next time, top of page 119. Okay? And we will go from there. Sorry you weren't here. I hope you'll be here Thursday. I sure hate to have to do this again by myself, okay? It's so boring. But we will do whatever it takes. So I will end the show now. Hope to see you Thursday.